Have you ever seen iron filings dance around a magnet or wondered how particle detectors trace invisible paths? That's the magnetic force at work. Now, when a charged particle moves through a magnetic field, it doesn't just keep going straight, it feels a sideways push. This push is the magnetic force, and it's given by the equation F equals Q into V cross B. Here, F is the force vector, Q is the charge on the particle, V is the velocity vector, and B is the magnetic field vector. It's a vector cross product, which means direction matters. And how do we find that direction? Use the right-hand rule, point your fingers in the direction of velocity, curl them towards the magnetic field, and your thumb gives the direction of the force on a positive charge. If the velocity and field are perpendicular, the force is at its maximum. But if they're parallel or anti-parallel, the force becomes zero. It's this directional twist that sets the stage for fascinating motion patterns in magnetic fields. Let's zoom in on one of the most classic outcomes, circular motion. Picture a charged particle, say an electron, entering a magnetic field perpendicularly. Immediately, it feels a force that's always perpendicular to its velocity. What does that remind you of? Centripetal force. So, instead of moving straight, the particle bends and bends until it goes in a circle. The equation that governs this is Q into V into B equals M into V squared by R. Solve for R and you get R equals M into V divided by Q into B. This is the radius of the circular path. The motion has a steady frequency too. Omega equals QB by M, which is called the cyclotron frequency. It tells us how fast the particle loops around the circle. As shown in the diagram, the particle's path curves smoothly under the invisible guidance of magnetic force without changing its speed. Now, what if the particle doesn't enter the field head-on or sideways, but at some angle? In that case, its velocity splits into two parts, one along the field and one across it. The perpendicular component leads to circular motion, while the parallel component keeps the particle moving forward. Put these together and what do you get? A helix. The particle spirals around like a spring as it moves along the field lines. The radius of the helix still follows R equals M into V perpendicular divided by Q into B. The pitch or spacing of the spiral turns is given by V parallel into time period. The tighter the spiral, the slower it moves forward, the wider the spiral, the faster. This beautiful motion isn't just theoretical, it's observed in cosmic rays spiraling through Earth's magnetic field. This helical motion of charged particles is far from useless. In fact, it's at the heart of some powerful technologies. In cyclotrons, we use circular motion to accelerate particles to high speeds, essential in medical and nuclear research. In space, Earth's magnetic field traps solar particles into spirals in the Van Allen radiation belts. And in fusion reactors like tokamaks, spiraling charged particles are trapped using strong magnetic fields to maintain high temperatures. Even in mass spectrometers, this curved motion helps us calculate the mass-to-charge ratio of ions. So whether it's in space, labs, or industrial setups, motion in magnetic fields shapes the future of science and energy. You might wonder, if the magnetic force is always acting, is it doing any work? The answer is, surprisingly, no. The magnetic force always acts perpendicular to the motion of the charged particle. Since work equals force times displacement in the direction of the force, and here that angle is 90 degrees, the work done is zero. That means the kinetic energy of the particle remains constant, only its direction changes. So magnetic fields can redirect particles without speeding them up or slowing them down. This is a powerful idea in physics: force without work, motion without energy transfer, a unique trait of magnetic interactions. Let's apply everything with an advanced numerical example. Suppose an electron is moving at 3 × 10 to the power 6 meters per second and enters a magnetic field of 0.01 Tesla perpendicular to it. What's the radius of the path? Use the formula R equals m into V divided by Q into B. Plug in the values. Mass of electron is 9.1 × 10 to the power minus 31 kilograms. Charge is 1.6 × 10 to the power minus 19 coulombs. We get R equals 1.71 × 10 to the power minus 2 meters or 1.71 centimeters. Now, let's find the cyclotron frequency using F equals QB divided by 2 pi m. Substituting the values, we get approximately 2.8 × 10 to the power 6 Hz. That means the electron completes about 2.8 million rotations every second. Just imagine, in less than a blink, it loops millions of times inside a magnetic field. Let's quickly revise what we've explored in this module. Magnetic force on a moving charge always acts perpendicular to both its velocity and the magnetic field. When the velocity is perpendicular to the field, the particle moves in a perfect circle. If it's at an angle, the result is a helical path. The formulas R equals mv over qb and F equals qb over 2 pi m allow us to calculate the motion dynamics. Magnetic fields never do work on particles, so their speed remains constant. And from particle accelerators to space science, this motion plays a crucial role. I hope this session helped you connect the dots between invisible fields and visible motion, from the spiral paths in space to the circular accelerators in labs. See you in the next class where we explore more wonders of electromagnetism in action.